Here are some more probability examples. So let's suppose events A and B are independent, and that's going to be important. Suppose event A occurs with probability 0.63 and event B occurs with probability 0.32. And our first question is, if the event A or event B occurs, what is the probability that B occurs? When you have this if part, it's a conditional probability, but we're trying to find the probability of B. So let's write it out with some notation. Here we have probability of B, that's what we're looking for. If that, that's our condition. We have that vertical bar straight up and down, given that, if that. Event A or B. So or is your union between two events. So we have in here A union B. And I'm going to draw a little Venn diagram. Maybe that will help us kind of picture what's going on with these two events. When you have two events, you always draw them with overlapping circles unless it specifically says they're mutually exclusive. So we have all of A, all of B. The intersection of A and B is this kind of football shape between, and A union B is everything. Now when we rewrite the conditional probability formula, we can write it as the probability of the first event intersected, that's that upside down U means and, the second event and then you divide it by what's your condition, the union in this case. So you need to kind of think about that top piece, is that A union B would be all of A, B, or both. Everything I have shaded in there. The B itself, go this way with a different color, is right in there. And we want where those two things intersect. And looking in here, where would be the hash marks going both directions? Well, that would be everything really just inside of the circle B that has hash marks going in both directions. So this whole thing up here on the top can just be simplified to be the probability of B. And that's a lot easier if you're looking at each one. Now, another piece that we'll need is the intersection. What's this probability in the middle? And we'll do that just a second. Let's start writing out this fraction. The probability of B was 0.32. So I know that piece. On the bottom, when we write out the union between two events, it's the probability of the first event. I'll actually write the whole thing. Probability of A plus the probability of B minus the probability of A and B. That's the definition of our union. And we have these two pieces for us, given to us, but we don't have the A and B. So this can be actually simplified. If we're looking, we still have 0.32 on the top. Probability of A was 0.63. Probability of B was 0.32. Now, you can only do this next step because it specifically states that these two events are independent. When two events are independent, by definition, the probability of A intersect B equals the probability of A times the probability of B. So we can replace this piece in here with 0.63 times 0.32. And again, you can only do that if it specifically states beforehand that they're independent. And if you slide that down, it gets to be 0.4276, and that would be your answer. Here's another one. Same scenario up on top here, with probability event A is 0.63 and probability B is 0.32. But I'm going to have part B. Given that A does not occur, what is the probability that B occurs? So here's another conditional probability. And we're trying to find the probability of B again. Our condition is just that A does not occur. And for complement, I'm going to use a little superscript C for complement. So probability B, given that A does not occur, looks like this. And we can, again, write that out as our conditional probability is the probability of the first event intersected with the second event, divided by our condition. Here's another Venn diagram just to look at what's going on there. Here's A, here's B. Let's look at everything that's not in A. I'll do hash marks going this way. So that would be not A complement. Everything in B is going that way. And we want where those two things intersect. So where are the hash marks going in both directions? And this little backwards moon shape. Right in there. Well, what would that look like? Well, there's a couple different ways to do that, but I'm going to look at all of B minus the intersection of A and B. That's the little football wedge in between there. Because we know the A and B from our previous step of our problem in here. So if we're looking at this piece in purple, that's the probability of A and B. Because they're independent, and only because they're independent, we can write that out as 0.63 times 0.32. Okay, that's a rule only because they're independent in that one piece. So now when I go up here, I would have the probability of B, this piece, which is equal to, what was B? 0.32, minus that intersection of 0.63 times 0.32. And then I'm dividing it by the complement of A. Well, the complement of A would just be 1 minus the probability of A. And the probability of A was 0.63. And I have to puzzle these little pieces together. And this will come out to be equal to 0.32. You could have actually done some other things and looked at solving this, and it's coming out to be the probability of B. There's always more than one way to go about these problems. Now, if two events are mutually exclusive, that's not the same thing as independence. So let's do an example real quick when two events are mutually exclusive and look at the difference there. So mutually exclusive events means that two events cannot occur at the same time. So let's suppose that A and B are mutually exclusive. Event A occurs with probability 0.12, and event B occurs with probability 0.17. And then here's our question. If A does not occur, what is the probability that B, I should say, occurs? So again, probability of B, given that, or if that, A complement we're looking for. So we have here the probability of B intersect A complement all over the probability of A complement. When we draw a Venn diagram for mutually exclusive events, the two circles do not overlap one another because they cannot occur at the same time. So again, if I'm looking at everything outside of A, right, and then here the B, the probability of B going this way. When I look at the probability of B intersect A, well, that's all of B. It's the whole. You don't have to subtract out that little football wedge in there. And you think about it, the football wedge would just be equal to 0. If the probability two events cannot occur at the same time, that means the probability A and B equals 0. So you're sort of like subtracting 0 out from the previous problem we had. So here, this one, the top would just be equal to the probability of B over 1 minus the probability of A. And our probability of B, I changed the numbers on this particular example, but would be equal to 0.17. And then we have 1 minus the probability of A is 0.12. Let's see. Comes out to be 0.1932. So it's helpful with these Venn diagrams sometimes. If you don't have context, you just have A's and B's to draw them out.